Walter Spitzer, and this is,
Olivier Donfack.
and we are doing the final fluid lab for mechanics of materials.
The objective of the lab is to design and apply an experiment to evaluate the physical properties, density and viscosity in our case, of a fluid in a pump system, and how forces are acted upon on this pump system. The forces in this case would be the pressure we apply to the top of the pump and the gravity which acts upon the fluid in the down direction. In this experiment, we will determine the following. 1, the flow rate of the fluid. 2, the pressure needed to produce a consistent flow rate. 3, the head loss of the pump system which the fluid travels. These will also be evaluated with the fluent program for accuracy. The apparatus of the system, we bought a 8-ounce bottle of instant hand sanitizer, CVS brand. We didn't buy the aloe vera kind because we wanted as pure a sample as possible. Now, this is a pump action system. There's a hose suspended in the fluid, which will suck the fluid. The top you press the pump down. This creates a vacuum inside the system and expels the fluid. In order to facilitate this, we were looking for a consistent flow rate from the tank down here to the nozzle out here and out. In order to do this, we get a weight. We will apply the weight to the top of this, a weight sufficient enough to produce a consistent flow rate. We will use a stopwatch to measure the time in which it flows, and we will reference that to the amount of fluid that is expelled. We use a scale to measure the weight of the fluid expelled, and we will use a tape measure or some sort of measuring device to measure the height difference in the fluid. This will reference the total volume expelled. We will also be measuring through a caliper the size, the cross-sectional area of the tank. This combined with the height will give us a volume of the fluid expelled. Combining with the weight, we will be able to produce a density. Now, for the procedure itself, first thing we need to do is determine the cross-sectional area, or rather, we need to consider the volume that is expelled during each pump. How we will do this is we will measure the cross-sectional area of the storage tank for the pump system, which is the bottle down here. We will take an outline of a square, illustrated here. Now, because this is round, it's very difficult for us to find the exact cross-sectional area. So this is largely a square. What we did here was we took the square outline and we considered the rounded portions over here that again do not exist over here. For the rounded portions of the total square outline, we will consider these triangles. We'll have the total area of this. We will consider the square and subtract the 4 triangles on each side. The result should be the total cross-sectional area. This is the height of triangle 1, width of triangle 1, divided by 2 times 4, and that sum subtracted by the total rectangle will produce a fairly accurate cross-sectional area. Now, as far as the other method of finding the height drop, what we have to do there is we have to measure the height of the fluid before each pump and the height of the fluid after each pump. Cross-sectional area times height difference will give us the volume expelled during each pump. Now, when it is pumped out, we will apply a mass of 2.5 kilograms on top. This is a known force applied to the vertical direction of pumping. It will expel an amount of fluid. This will be weighed on this scale over here. We will take this weight, we already zeroed it out to factor in the paper towel, which we will consider as a retaining containment as seen over here. We will measure the weight of the fluid expelled. We will have the density from the weight of the fluid expelled by the volume of the fluid expelled, which I just explained in part 1 and part 2. This will produce the density. Now we also will take the time of the fluid expelled. This will allow us, with the volume, to calculate the flow rate. So in conclusion, we will be collecting the total dropping time, T, record the height difference, D, record the mass of the fluid exerted, which is what we will use weigh on the scale. We will repeat step 4, this step, 3 to 4 times in order to obtain a fairly accurate description and to make sure our results are consistent, and we fully expect they will be. Here, we will take Olivier is taking the initial height of the fluid. Olivier, what is the initial height?
8.5.
8.5 centimeters. Now with the initial height noted, we will apply the weight. We will place the weight first. He will coordinate with me, and then we will apply the weight. He is laying the drop cloth now. This is the paper towel with the known mass, which we will put on the scale in order to obtain. And once the fluid is on it, we will weigh it, noting the weight of the paper towel, and then we will find the weight of the fluid expelled. Now, with our stopwatch, we will drop it. On the count of 3, and note he is not supporting the weight of the actual weight. He is not supporting it. He will merely guide it down so to balance on it. His main focus will be on applying pressure in the X direction as to not affect the force. Olivier, press down on the drop the weight, please. On the count of 3.
1, 2, 3.
With this fluid expelled, we will weigh this fluid in order to obtain the properties such as density. It was noted that this fluid is very viscous, and to minimize the effects of this viscosity and the possibility that this might cause the fluid level to be inconsistent, hills and valleys, in between each measurement, we will try to even it out by shaking up the fluid clinging to the walls. This will flatten it out to some extent and minimize possible errors. Here, we are balancing the scale with the fluid on top to obtain the mass of the fluid expelled. Looking at the 4 runs that were practiced, we see that the mass of 3 of the 4 runs produced 0.9 grams of fluid. Given that the numbers 2, 3, and 4
are very consistent, we consider run 1 an outlying condition and consider the mass to be 0.9 grams expelled. The average time is 0.488 seconds. We assume that to be the time. The average height drop for each run is 0.5 millimeters. To find the density, first we find the volume. The volume is the difference in height times the cross-sectional area. Plugging in our values that we had found earlier, the difference in height averaged to 0.5 meters. The found cross-sectional area was 0.0022 meters squared, giving us a volume of 1.1 times 10 to the negative 6 meters cubed. Our density, mass divided by volume, will be 0.9 grams divided by our volume, 1.1 times 10 to the negative 6 meters cubed, giving us a density of 8.18 kilograms divided by meters cubed. Now we find the pressure due to the mass applied to the pump system. The diameter of the hose is taken. From this we calculate the area, the cross-sectional area of the hose. We take the mass of the weight times gravity divided by area, and from this we obtain the pressure. The pressure contribution from the gravity for the fluid in the pipe can be found as followed. The formula is P gravity equals density times gravity times the difference in height. We do this in the formula as follows. When factored into the total equation, considering that the pressure due to the fluid in the pipe is acting in the opposite direction of the pressure of the mass applied, the effects are negligible and there is no difference, no significant difference.
Hi, my name is Roynard Storey. I'm a part of the group, and this is our analysis from Fluent.
And here is Olivier Donfack for the final exam fluid, and we're going to show you how we run the final exam through Fluent. Thanks.
So here is our pipeline that we've created, and the height of it is right here. It's set 16 centimeters, and the diameter of it, which was created, was 0.0042 meters, but we had this, since we split it in half, we created it to be 0.0024 meters. From there, we did the edging of it, and for this edging here, we made divisions of 10 for the top and the bottom, and then for the edges from side to side, we made them 100 divisions. So after we created our geometry and our mesh, we put it in Fluent, and we went to solution setup, and from solution setup, since the pipe is vertical, we put the gravitational acceleration in the y direction, which is negative 9.81 meters per second squared. From there, we went to materials and fluid, created the fluid, and we calculated the density, which was 818 kilograms per meter cubed, and the viscosity, which was calculated, which was 0.007 kilograms per meter second. After we created and changed that, we went to boundary conditions. From boundary conditions, we made the boundary conditions at the center line, which is right here. From there, after we did that, we went to solution initialization. From solution initialization, we initialized it. We hit OK. From there, we run calculations, and we calculate it. We hit OK. We go to graphics and animations. Then in the graphics part of it, we went to setup. From setup, we went to display. And in that display, we found out that the pressure of it was
When evaluating the head losses through causes other than the difference in pressure, we see that because the length, distance, and velocity of our fluid in this experiment, of our pump system, are very, very small, major losses will be incredibly small in comparison to the 6.35 times 10 to the 5 of our pressure, making them a nominal factor. Likewise, the minor losses, because they depend on a very small velocity, will also be a very minor factor. By this definition, we will simply look at the difference in pressure as the source of our head loss. When comparing the results for pressure difference, or head loss in this case, using the results from the hand calculations or the experiment and the results from the fluid program, we are able to see a profound difference, a difference of approximately 94%. Possible causes of this are mechanical resistance in the pump system itself. The pump system there must be force applied to the pump in order to power the fluid expelled. I believe there is also a spring in the pump which causes it to rebound. This force must also be overcome in order to expel the fluid. There is always the possibility of computational and measurement errors as well. In this lab, we evaluated the properties and behavior of a very viscous fluid, hand sanitizer, in a pump system. By applying pressure and measuring the result of this pressure, the mass of the fluid expelled, time, and other properties, we were able to determine the mass flow rate of the fluid, the density, the pressure inside the pump, and other properties. Through evaluations, we found that because the fluid is so viscous and causes such a high pressure, that the main contributor to head loss is the pressure difference itself, or the viscous fluid in the system. The force due to shear force from the friction inside the pump system is nominal. The force due to angle change is nominal. The force due to gravity acting on the fluid is nominal. We see here that the higher the viscosity is, the less it depends on outlying forces.